Let's get started. And you may remember on Monday, we were talking about guilty versus innocent. And there's that concept in many legal jurisdictions where you are innocent until proven guilty, where you need overwhelming evidence for your peers or for a jury to reclassify your innocent guilty status from innocent to guilty. Why were we discussing this concept? I mean, what does it have to do with statistics? We mentioned the idea of a null hypothesis. We're not looking at the book right now. These are my old actuarial notes. This is the old CT series. These days, this material is, I would imagine, covered in CS1, core statistics, the first module. Back when I started writing the exams, it was CT3. Most of my colleagues had an exemption since they had a background in statistics from their years at university. I had to do it, and it's when I first gained this familiarity with the idea of hypothesis testing. And as we do best in these sessions, we're going to read the basic hypothesis being tested is the null hypothesis, and standard notation is H0, and it is sometimes regarded as representing the current state of knowledge or belief about the value of a parameter. And we mentioned status quo on Monday being tested. In many situations, a difference between two populations is being tested, and the null hypothesis is that there is no difference. So for instance, take two populations of students. One group of students is learning the usual way. Think of it as the traditional way. But with a second group, you decide to use virtual reality, for example. You perform the lessons, you expose them to this new teaching method, say over a 6-month period or a semester or an academic year. And what you're really interested in is there a difference in perhaps their performance, in how likely they are to choose that subject at sixth form, these kind of impacts that can be measured either by a test or giving them a survey. And this is what we mean by the difference between two populations. For instance, you look at the mean of both populations. You look at the mean mark of both populations. You look at the variance of both populations. In a test, the null hypothesis is contrasted with an alternative hypothesis. These notes denote it as H1. The book writes it as H subscript A. A test is a rule which divides the sample space, the set of possible values of the data, into two subsets. A region in which the data is consistent with H0, and its complement, its negation, in which the data are consistent, or rather inconsistent this time around, with H0. The tests discussed here are designed to answer the question, does the data provide evidence to justify our rejecting H0? Meaning, when we're hypothesis testing, and just to get an idea of hypothesis testing, let's go back to the very first time that this book mentions hypothesis testing. And if we're going to do that, probably a good idea to first go to the first page and then search hypothesis. And this is exactly it. The very first instance of hypothesis testing in the book occurs in the simple linear regression that we've been discussing from the very start of the sessions this week. We're estimating beta naught hat and beta 1 hat, and then it's from that point onwards, it's very natural to ask, is there in fact a relationship between our single predictor variable, uppercase X, and between the output we're trying to predict, uppercase Y. The null hypothesis, the status quo, the innocent until proven guilty, is that you assume no relationship. The alternative hypothesis, H1, or else HA over here, is that there is some relationship. And of course, then if there is a relationship, you would want to quantify it. And beta 1 would be the true relationship, the rate at which Y changes, either increasing or decreasing, as you increase the value of X. Are they, to a certain extent, directly or positively correlated, or are they negatively correlated? Is the slope negative? My idea was that before we actually go into hypothesis testing, I'd like to do something similar to yesterday's session. Now, what was yesterday's session? It was where we were discussing unbiased estimators. What is an unbiased estimator? Well, we usually infer, we usually deduce quantities or summaries of a population of data subjects. So think of everyone who intends on voting in our next general election by only surveying, interviewing, collecting a smaller subset of the entire population. This is what we usually refer to as the sample. Now, the sample is going to have, to one degree or another, an element of bias in it. So calculating the mean of your sample, while it may give you an idea, or you may use it to get an idea of the overall population mean, we would certainly be optimistic to assume that is going to necessarily correspond exactly to the population's mean. And there's this concept of creating unbiased estimators. What is an unbiased estimator? That you're kind of looking at it on two levels. You have, instead of one single sample data set, you have multiple data sets, multiple samples. You calculate the mu hat, or the estimated mean, for each of those sample sets. And if it's an unbiased estimator, the mean of those means should equal exactly the population mean, because you have certain samples where the mean is underestimating the true mean, the population mean. Similarly, there'll be other data sets, and you're hoping that they kind of cancel each other out. You're kind of hoping that as much as you're overestimating the mean in one sample data set, you are underestimating it in another. And what I'd like us to do over here is something similar, but I would like to create, just before we do this hypothesis testing, I would like to create an interval of beta 1 hats. So what do I mean by this? In practice, you will usually only have a single beta 1 hat from your data. And then you create a confidence interval by calculating the standard error, which we concluded yesterday's session by remarking that this would actually itself be an estimate, since it depends on sigma squared, which is the random errors variance, which you wouldn't know usually in practice. And instead we estimate using the residual square error? It was the acronym's RSE, the residual standard error. And then it just so happens that if you want a 95% confidence interval, if you want to be able to go to the board or a committee and you're presenting your findings, and this is usually what actuaries do, there is a clear difference between the decision makers and the individuals that are informing those decisions. And that's what you want. It's also part of an audit trail. It's considered good governance, where in an insurance company, to take, perhaps in my case, the example, the scenario I'm most familiar with, you have your actuaries. If you think of it as a hierarchy to a certain extent, or a flow chart, you have the group chief actuary who is instructing his or her actuaries to do certain studies, build models, aggregate data, clean the data, not necessarily in that order. They prepare a report. Usually the group chief actuary signs off that report. So you have their signature, you have their sign off. Then that report is presented to a committee. So for example, a pricing committee, a reserving committee, a capital modeling committee, claims committee, underwriting committee. These are 5 of the most important decision-making components within an insurance company, and it's quite similar beyond insurance. And that committee will then recommend to the board. So finally, it's always the board that's answerable to the shareholders, but you have this entire process where the actuaries or the data scientists are producing their findings, and they're not giving what we call a point estimate. They're not giving if we can just undo, the pink would be the point estimate. That is your estimator. It's a single linear regression. This is the slope. That's not enough. Any seasoned committee member or member of the board, they're naturally going to ask, well, okay, this is all well and good. What are your margins of error? What is your confidence interval? What is the risk that you're expecting me to, well, first of all, comprehend? And secondly, if let's say it's a pricing committee and the actuaries or the chief actuary is advising we should sell this new product, we should in the first 2 years set these prices to these different segments of policyholders, and you're going to suggest a recommended price. So pet insurance for this type of pet on an annual basis with a limit of 5K a year should be priced at 100 euros, for instance. Now that's your best estimate. That's your best estimate. You usually go a step beyond that and you give, well, first and foremost yourself, and then anyone who's going to use that advice, anyone who's going to actually take decisions on the basis of your findings and conclusions. Usually the report would have an executive summary, and in half a page, you should be able to lay out everything, have a bit of an actuarial best estimate within it. And this is where these plus and minus standard errors come into play. I've placed that hat because that standard error itself is unfortunately an estimate. We're multiplying by 2 for the simple reason that I think we're assuming normality somewhere. And if you multiply by 2, those of you who are familiar with the normal distribution, the bell curve, 2 standard deviations, we could see this in my browser. I think it takes you to roughly 95, I think it's just over 96%. So let's quickly look at this. We can get rid of these tabs. I'll keep this one. We might discuss it today. And if we do normal distribution, and we're speaking of standard errors, how far away you are from the mean. Yeah. So it is in fact actually 95%. Don't ask me from where I got that 96%, but close enough. So two standard deviations away from the mean captures 95% of the likely, or of the possible, I should say, of the possible outcomes. Now, if you want it to be 99.7%, and by the way, that's very close to Solvency II. So Solvency II regime, insurers are expected to be capitalized. They're expected to have enough of a buffer when it comes to their assets over liabilities of 99.5%. So many ways you can think of Solvency II regime. It's a European Union directive that really sets out practically every aspect of how insurance companies operate. Then that capitalization is your confidence interval that the company doesn't fail, that the company is able to pay out its insurance claims. That confidence interval has a width of 3 standard deviations either way. You can think of your mu as your balance sheet. So the balance sheet is what you're expecting. But then you say, well, my assets could lose value in the next 12 months. Solvency II uses a 1-year time horizon, which is why I'm mentioning 12 months. So you say, well, my assets could lose value, my liabilities could be underestimated, my balance sheet, and actually that would be what if we just search for a balance sheet? What if we do, for example, Bupa, and there's something called an ORSA. And let's see. No, the ORSA isn't public. You know what is public? Not the ORSA, not the ORSA. This has to do with Pillar 3 reporting. SFCR, SFCR. And we'll probably be able to download it. We could look at, yeah, I just took Bupa as an example. So where is Bupa's SFCR? Let's see. Maybe we'll delete Pillar 3. We'll do this. I'll just give you an idea of what their balance sheet looks like. Look, so Bupa, we've heard of Bupa, right? It's one of the major health insurance providers. Do I need to accept? Yeah, we'll just save preferences. And we can look at their most recent one. Now, let's look at the group, for instance. This is their SFCR. Usually, okay, it's not too detailed. Normally it's signed off, but anyway, let's look at their balance sheet. Let's look at their balance sheet. So let's have a look. Let's have a look. So what if I type balance sheet? Here we go. So look, number one, notice there are two different valuation bases. What do I mean by valuation bases? Well, in just very simple terms, let's say that you're selling your car, you value it at so much, but when you actually speak to an expert, and again, even experts will disagree between them. What is an expert, after all? Anyone can call themselves an expert, but maybe we assign more value to their own estimate or valuation. It's just the different ways, different principles, different standards for valuing assets and liabilities. There really is nothing else, right? Assets and liabilities. So let's look at Solvency II. So notice, for example, Solvency II, you're not allowed to recognize any goodwill, which is kind of, how just think of the reputation, the value of a company's brand. Let's take, for instance, something really simple. Let's take their cash at bank, and I imagine this is in millions, so quite a nice position, right? You have 1.5 billion in liquid cash. They're ready to make take advantage of any maybe investment opportunities, to pay out claims. This is the balance sheet. But what is the balance sheet? What is the balance sheet? The balance sheet is just your expected. Your balance sheet is your mu. The accountants have basically just cash is very simple, right? You just sum up what you have in your various bank accounts. Now, what could go wrong? What could go wrong? Well, I could have cash in a specific bank, with a specific bank, and that bank goes under. And there might be deposit guarantee schemes, as we have in our own country, but those are only up to like the first 100K. Anything above that, and who knows, maybe even the depositor guarantee won't pay out. So you stress your assets downwards. You're looking at the worst, not the worst case scenario, but you're looking at when it's this kind of analysis from the point of view of a regulator would want to know to what extent could this be overestimated because it's an asset. So you want to be, what's the word? Not prudent. You want to just, what's that phrase when you want to be on the safe side. So you can stress your cash downwards. I know this has nothing to do with modeling, but hopefully it's giving you maybe, we're just getting some exposure over here to where we would speak of confidence intervals in your day-to-day office work. Now, and this is where actuaries come in. Actuaries, the joke we've often repeated it, is actuaries are more comfortable with liabilities than with assets. Many of the techniques that we learn are in fact for valuing liabilities, specifically insurance liabilities. What is an insurance liability? If I owe you 100 euros, is that an insurance liability? No, I owe you 100 euros, plus maybe some interest. An insurance liability is when you have liabilities that at their very core, they are intrinsically tied into what we call contingent events. You may have heard of contingent events if you ever had history as well. Contingencies, things that didn't necessarily happen, things that weren't guaranteed to happen, contingencies. So if we look it up, an event that may, but is not certain to occur. This is what actuaries are looking at, right? The likelihood of these events occurring, at what frequency, if they occur, what is the impact, the financial impact, and the timing. So actuaries, at least in non-life, look at three major sources of uncertainty relating to what we refer to as technical provisions. It's a provision. It's not like a payable. A payable, okay, so Bupa at year end had to pay 409 million to perhaps members of staff, maybe regulatory fines if they were fined in any way, construction costs. Bupa has its own kind of healthcare centers, so it's vertically integrated. That's not a provision. That you kind of know that down to the last cent. It's not really based on contingent events. On the other hand, technical provisions, and that's D2. I wonder if it goes into more. I wonder if it goes into more detail. So what if we look up D2? D2. So the technical provisions for Solvency II purposes are an estimate. They're an estimate. They're an actuarial estimate. And in the balance sheet, you will see the actuarial best estimate. And all we mean by best is not it's superior to another estimate. It is the mean. It is the mean of the cost at which insurance contracts could be transferred to another knowledgeable insurer in an arm's length transaction. In fact, here we go. Look, the abbreviation is BEL, and it is the best estimate liability. And let's see if, do they throw in any probability jargon? Not that I can see, but if we type, for example, expected, you would imagine this word to be thrown around quite a bit. Oh, here we go, in this paragraph itself, and it occurs in other 33 times apparently. So it's what you are expecting, your expectation. Expectation in statistics is the same as the mean. And the idea is that although in your balance sheet you have a point estimate, you have a single value, in all likelihood, that value is wrong. Now, it could be off by €1, or we're probably measuring in sterling over here, given that it's Bupa. It could be off by £1. It could be off by £1,000,000, and in either direction, right? In either direction, although the regulator is most interested in the adverse development scenario. By how much could this value increase? And can this insurance company withstand such an increase? So imagine probably COVID to a company like Bupa, unless they had certain exclusions in their policy terms and conditions, well, it was probably impacted. It was probably COVID may have even been an existential threat to the company. Okay, so confidence intervals, presenting your results to a committee or to your superior, a member of the C-suite. And these confidence intervals are based on the standard error. Now, my idea was that we would do something similar to yesterday. Yesterday's session, we did basically no regression, but we were only working with data capturing a single variable. I think it was the heights of 5,000 individuals, but it was 100 individuals at a time from 50 data sets. I'd like to do something similar today, and we'll see where it takes us. But this time around with X and Y. So to do that, we'll just say that we have some kind of relationship. We'll say we have a linear relationship where A is 5 and B is, for instance, 9. These are going to be the true intercept and the true slope. We also need an error term. We need an error term, and we need to give it a mean and a standard deviation. So we'll call it error mean. We'll take it as 0. We'll take its error standard deviation, for instance, 11. And then we'll say, let's say X and we'll just generate some data. So uniform, we'll take 5,000 of them. But these 5,000, I'm going to subdivide them like yesterday into packets into data sets into 50 data sets, each data set containing 100 of these observations. We'll say between, for example, 20 and 60. Okay, just give you an idea. Okay, whatever these X values are, hours worked in a week. You're looking at everyone who has, at the very least, a part-time weekly contract of 20 hours. And then you have individuals that work overtime, entrepreneurs, self-employed, etc., etc., or who knows, maybe they have more than one job. So that would take us up to a maximum possible X observation of 60. Okay. You could do some summary statistics on X if you like as well. I'll call this X raw data. Now the Y raw data, you would normally collect this as well. What we're going to do instead, we're going to generate it. It's synthetic data. And we'll say A plus B times X. Now, if I stop here and I plot, then everything is on a line. And of course, that makes absolutely no sense. But now that we do it like this, oh, this isn't working either. Why? Oh. Now, wait a second. Why is it like that? Ah, because x has no value, right? I should be doing x raw. And hopefully this works now. There we go. So we're seeing 5,000 observations without an error term, they all fall neatly on this line. What's the equation of the line? Y equals 9x plus 5. 9x plus 5. Instead, we're going to include an error term. I'm going to have it follow a random, forget about the word random. I'm going to have it follow a normal distribution, R norm. And we need 5,000 of these with a mean of 0 and standard error of 11. We run it again, and now this is the data. This is the data. Can I make it larger, just so you have a better look at it? This is our raw data. We could maybe, to make things a bit more interesting, we could increase the standard error, perhaps. Do it 30, for example. And now it's like this. I mean, there would appear to be a clear correlation, positive correlation, right, between the y and the x, and it looks linear. At least these 5,000 observations would appear to suggest linearity. Okay, so we've done this kind of work several times. What are we going to do different today? Today, we're going to partition it into 50 datasets, and we'll create beta naught hat and beta 1 hat for each of these 50 datasets. First of all, I need a data frame, and we'll call it the raw data frame. And we simply do data frame, and very, very easy, very, very easy. There are a lot of other things that we could specify, but I'm just going to have this. Notice that we now have, besides these values in our global environment, we also have a single data set. But like I said, the idea is that instead of taking the raw data all at one go, I'm going to take, for example, the first data set will be just these 100. So imagine that in actual fact, you only have these 100 observations, whereas theoretically, maybe things would have developed in such a way that you wouldn't have had this data set, but you would have had another data set. And this is what we're trying to communicate to the board, that we have our data set and we've generated our B1 hat and our B0 hat, but we calculate the standard error to give an idea of the uncertainty, or to what extent it is an estimate of the true beta 1, of the true beta naught. So we're going to do this 50 times. We're going to have 50 beta 1s. And the way we do it is this. We'll say estimated beta 1. And this is just the null set for the time being, just like we did yesterday. And if I want to repeat something 50 times, it's the for function, dummy variable, I'll take k, 1 to 50. And now what am I going to do? Before I do any of this, let's just look at how you would estimate beta naught hat and beta 1 hat based on the first dataset 1, which contains the first 100 of these observations. It's very straightforward. There's the lm function. It asks you for the formula. You're going to regress y raw data on the x raw data. You give it the data, and the data is raw data, but only the first 100. So think of it as only having these 100 observations. And that's it, right? That's it. And we have numbers close to what we would expect. No, not really, right? This is fine. This is fine, 8.5. This is really off. Weren't we expecting... This is not what I would have expected. Unless it's at 20. Because at 20, that would make sense, right? It would be... No. Huh. That's funny. An intercept term of 26 point... I'm clearly missing something over here. If you think you know what I've done wrong, do let me know. We're regressing y on x. Huh. That's odd. Isn't a 5? So why is our intercept not close to 5? Anyway, I think we're going to have to live with this for the time being. How very odd. How very odd. I don't think this is going to make a difference, right? Oh, and now it's 2.13. Oh, really strange. Oh, wait, but these now have changed, haven't they? Now that I ran it, I should have probably set seed. I don't know. The set 1000. It makes no difference. 567. Let's try it again. Okay. And if we do it again, it should give the same. Why isn't this working? So we have, oh, because I need to set another seed over here so that it doesn't, so that each time these are the same values. I don't know, set seed for 1, 2, for instance. So we have that, and if we run it again, it should give us the same values. And now we have the same values, 1.191 and 9.020. I'm still not happy with this intercept. I was expecting, and I clearly this must be some kind of limitation in my understanding. I was expecting an intercept of 5. How very strange. Is it just the standard error? If the standard error was significantly lower, say 1, would we then get... Yes, interesting. Interesting, right? So that error term, the larger the error term is, it's not really going to impact your slope, just because the error terms kind of cancel each other out to a certain extent. But with this 30, with a much larger standard error, So what was it before? So earlier it was very close to 5. Now it's way off 5. So that error term really distorts the true y-intercept. Okay. Now, what do you do to only get the beta 1? What do you do to only get the slope? Do you see how we have this ln? We're using this to estimate the 2 parameters. Well, you do $, and unfortunately, when you tab, nothing comes of it. But you can type coefficients, and you could say just the second coefficient. And now we have just that value. If I delete this, something that we kind of stumbled across yesterday was if we type model like this, if you type view model, it opens another tab, and it's giving you the text is quite small. I'm not entirely sure how to make it larger. But you will see, look, residuals, effects, and the coefficients, it's a vector. And it contains these 2 values. And what happens if I... Oh, interesting. It's typed this. Model, square brackets coefficients, and then x row. Okay, so it's going to do the same thing, I guess. It's just a way of calling them, I guess. Okay. Let's delete this. Let's delete the view line of code. And we're back over here. The one thing I don't know how to do, it's not that important, but the one thing I don't know how to do is how to remove the name. So, yes, questions?
Just a small thing. The line 16, what's the LM for?
LM means linear model. And whenever you're not entirely sure in R, just type $LM. And if you run this single line of code, you will have the documentation over here. Usually there are examples as well at the very end. Not always, but it would appear to be the case over here. And it explains exactly what that function does, what the arguments are, formula, data. And what we're doing is we're creating a linear model. Specifically, it's a simple linear regression. 1 predictor variable, the x row. And you are estimating what it does is it performs these 2 calculations. It estimates the slope estimator and the y-intercept estimator. Y-intercept, so when x is 0. I don't know if that helps.
Yes, thank you, sir.
Okay, very good. So all it's doing, all that the LM is doing is it is giving you a line that attempts to describe this data. So you would imagine, I don't know, it's probably going to give us a line like this, roughly. Okay. Now what we're going to do is we're going to do this LM 50 times. Why 50 times? One time, once for each data set. And each data set is going to give us a different estimate for the slope. Okay. So let's have a look. Let's have a look. By the way, can I show it to you just to get a better idea? Yeah, okay. So for example, this is your first data set, these 100 observations. Your second data set is from 101, just the way I did it, until 200. So let's look at the second data set. Okay, eyes on this chart. I'm going to run it. That's the second data set. Then there's the third data set. Then there's the fourth data set. Then there's the fifth data set. All of them have, to one extent or another, certain biases. They're not capturing the entire population. Okay. Now, what are we going to do? Well, we're going to run the LM. We're going to run the LM. We're going to save the second coefficient, which is the slope parameter, beta 1 hat, as, I don't know, beta 1 hat, beta 1 hat. And we need to tell R, you shall first work on the first 100, then the second 100. And we did this yesterday, didn't we? We did this yesterday. It's quite simple. All you say is, it's an arithmetic progression. And if you remember your arithmetic progression, the nth term is first value plus n minus 1 times the difference. So 1 plus 100 minus 1, k minus 1, excuse me, times 100. So for example, when k is 1, you will get just 1. But when k is 2, you'll then get 101, because then it's going to be this one, from 101 to 200. Now, we need to give it until what? Until 100k. Until 100k. And the very last thing is to recycle this vector and save within it the previous iteration of the vector and include this estimated beta 1 hat. So let me run it, and we've ran it. The one thing is I want to learn how to remove the name of a vector. So R remove name from, yeah, remove row names. Yeah. Is it unname? Is it unname? So what if we do unname? Are you seeing each one is labeled extra coefficient? Is it a double N? Yeah. Unname. Yeah. These are our estimated beta 1 hats. One for each data set. Now you'll never have this in real life. In real life, you'll have one data set, you'll use it, and you'll create your beta 1 hat. What the confidence interval is doing, it's telling you, but what if you had multiple data sets? What if you had multiple data sets? You wouldn't get the same beta 1 hat for each data set. And this is what I've tried to show you over here. You can sort it. You can sort it. In ascending order. You can do it to 1 or to 2dp. And you can summarize it. Look. So remember when we had just the first data set, the first 100 observations, and we had our beta 1 hat of 9.02. Now we can see it within this context. So it was maybe closer to the right than to the left, but we have an interval over here. Now, the more data sets we take, the wider that interval might get. It can never get narrower, but the wider it gets. 95% confidence interval is saying if you had to do it infinitely many times, which of course is impossible, but theoretically speaking, if you had to perform this exercise infinitely many times, and what do I mean by this exercise? Get a data set, estimate beta 1 hat. Get another data set, estimate beta 1 hat for that data set. 95 out of 100 times, your beta 1 hat would be within this interval. Whereas in our case, I could, for example, very quickly give you a 50% confidence interval. What is the 50% confidence interval? It's between the first quartile and the third quartile. Can I show to you using the box plot function, which is something I don't think we've ever mentioned over here. Box plot, this entire thing. Look. So we'll draw these at O level. Maybe we'll draw them horizontally. And there is a way. I'm sure you don't want me wasting too much time, but there is a way. There is a way. Horizontal, do we tell it true? I don't know, maybe you prefer it this way. Notice this might be an outlier. Now we'll see. And if we color code everything, the 50% interval, is between 8.852, you see it? 8.852 over here. And 9.155. So you could go to the board and tell them whichever two variables you're attempting to find a relationship for, you could tell them we have a beta 1 hat of 9.01 9.01, but there's this 50% confidence interval. We expect that 50% of the time, well, should I say it that way? I'll say it that way. It's not maybe not the best way of saying this, but 50% of the time, or you could expect with 50% confidence that it is within this pink interval. Now, of course, you can create you can give them larger confidence intervals. You could maybe the 95% confidence interval would be this. But please do keep in mind, you can't do this in real life. This is more just to get an idea of what the book is doing. You can't do this in real life. Why can't you do it in real life? Because in real life you have one data set. That's it. One data set. You won't have multiple data sets. If you had multiple data sets, you put them all in one data set. And even so, however large your data set is, it's never going to comprehensively reflect all the theoretically possible outcomes. Even if you look at every single insurance claim ever in the history of the product, tomorrow there might be a claim with specific features or specific circumstances that have just never occurred. For example, there was one claim, was that it was a person who claimed they got an STD from having sex in a car, and I think they successfully, I don't know how successful they were. I'm trying to remember the insurance company. If we and it wasn't all, was it Allstate? Allstate. Well, I'm not gonna type, but anyway, so that's one of those claims that company would have never faced. A very strange one, right? It was on their motor insurance. So how on earth is the insurance event in any way covered by a motor insurance policy? By the way, you can imagine how they quickly changed the contract wordings of every policy that was sold after that claim was filed. It's all about having, watertight policy wordings to avoid these odd situations. So in real life, you'd only have one data set. You need to think of that data set as only one of theoretically and infinitely many different data sets, all with their own biases, which is why we use this formula, to estimate the confidence interval. It would be really interesting. We don't necessarily need to do it today. I realize we are quickly running out of time or have already done so. Really interesting if maybe using this formula, we see if we can get what is the standard error? What is the standard error? Sort of like the difference between the mean and the maximum, isn't it, right? So one very, very last thing, If I save this as vector z, and I do max Z minus mean of Z, we get this distance. We get this distance. So it's what? It's 9.45 minus roughly 9, which is 0.45. And then maybe we have to divide it by 2, because you'd normally get this by multiplying the standard error by 2. So if I reverse it, this is probably the standard error, roughly. And can we just, and this would be the very, I promise, this would be the very, very last thing that we do. Can we see if we get a similar number by doing the square root of all this? Notice I can't cancel the square root with the square, because this is summation. So just very, very quickly, very, very, very quickly. What if I say square root of the standard error of the error term, the standard deviation, excuse me, the standard deviation divided by the sum of x raw minus the mean of x raw squared. No, it's actually very different. It's actually very different. We're off by an order of magnitude. So I clearly that's a pity. That's a pity. So my intuition doesn't seem. No, looks like I typed it correctly. So what's interesting is that if I've calculated this correctly, then the standard error in beta 1 should be only of 0.03. But when you multiply this by 2, you definitely don't get this. We're off by an entire order of magnitude. So it's maybe something we'll look into next session. But we'll call it a day. Thanks.